Anybody got any issues with anything you ran into on those first two reviews on circles or parabolas? Anyone?
Like the semicircle stuff? Is that going to be?
Okay, good point. We did not talk about that. I actually remembered to talk about it 7th period, but that didn't do you any good. So for semicircles or semi-anything, let me give you my advice on that. So a semicircle could look like any one of these things. Say it could be this, and this is the one you kind of learned on your 19 basic functions. Remember that? So it might look like that, but, and if it does look like this, what does your semicircle look like? Looks like this, and what's the radius of it? It'd be 5, right? So you kind of learned that already on the 19 basic functions. That's the r squared. So up 5, over 5, left 5, and you just sketch your little semicircle in there the best you can. What if it is that? And obviously a negative reflects that, and it looks something like this. What if it is this, though? So that is going to be opened up, not up or down, but to the right or to the left. Which way do you think this is going? To the right. Now, is there a way to remember that in your head without memorizing? Yeah, if you think about this, this is just an equation for points, right? I plug in a y, I get an x. I plug in an x, I get a y. That's all I'm doing here. But according to this, the x values that you will get have to be what? Positive. And where do x values that are positive show up? In the first and the fourth quadrants, right? Same thing here. Y has to be equal to positives. That can only occur if I'm going up. That occurs in the first and the second. This, y has to be equal to negative values. That can only occur in the third and the fourth because I'm going down. And then finally, if I get an x equal to negative, and this is important that what I'm saying here because I'm about to get even dirtier with this when we get to ellipses and hyperbolas. So in something like this, you recognize, oh yeah, that has that semicircle look to it. So x would have to be a negative number, and if x is negative, it's going to head this way. Now you're about to get them where they're not just circles, and they're going to be all mixed together. So my advice to you is, if you don't know immediately what it is, which I gotta be honest with you, you're probably not always gonna see this. Because you're gonna see stuff that has a 2x squared or 4 or a 9y squared. You're gonna go, wait a minute, what is that? My advice to you is if you're not sure what kind of figure it is, and that might be negative, it might be positive. If you're not sure what it is, square both sides. If I square both sides here, I get y squared equals 25 minus x squared. And then if I just add the x squared over, that's a circle, right? Now that doesn't mean your equation is a circle. It means that if I square both sides, which, you know, when you square stuff, like if I tell you that x equals 3, and all of a sudden you go and square both sides, now I have something where x could be plus or minus 3. So you know when you square both sides, sometimes you introduce extra answers in there that don't work. So this will give you the general look of it, right? It generally is a circle, but then you got to go back to the original and go, wait, y is positive. Where do y values occur positively? Up here. Same thing here. If I square both sides, okay, we'll go down here. If I square both sides, I get x squared equals positive 25 minus y squared. And if I add the y squared to the other side, are you seeing that it looks like a circle? So you could think, oh, this must be a circle. But wait, back to the original problem, x must be negative. That kid gives me just the left part, so I get rid of the right part. So do that whenever you're seeing stuff that's weird like this, and you're going to see stuff tonight and tomorrow that isn't a 19 basic function, that does look a little weird, and you might not know whether it's a circle or an ellipse or a hyperbola. That's okay. Just square both sides, figure out what it is from that, which you'll be able to do after today. I'll hopefully remind you about all that stuff, and I'll try to do a problem like that. And then after you square both sides, you'll have a general idea what the graph looks like, so you can sketch it. And then you go back and go, oh yeah, x is negative. So just keep where the negative x's occur. So hypothetically, what if you had found out it was a hyperbola on this thing? And you go in there and you sketch it and you get this. You get some hyperbola. And then you go back and go, oh yeah, x would have to be negative values. That's the left side. And you would go back and just get rid of that. Or what if you found out that it was an ellipse going up or down, right? But then you go back and go, wait, x is negative. It's just going to be the left part, the part that has left negative x's. So that's the whole idea on these. But the best thing you can do probably to be safe, square both sides, make it look like one of the conic sections, and then you'll have a better idea what it looks like. You got tracking with me? Okay. All right. So let's take, you sure there's nothing else about circles or parabolas that you ran into that you want to talk about? How do you graph them when the a value is like 3 or 5 or 7 or negative 12? Cheap trick. How do you graph them when it's like 1/12 or 2/19 or something like that? And how do you find the lattice rectum? Flip the A. And how far is the lattice rectum from the vertex? C. And how do you find C?
1/4.
You take 1/4 of the length of the lattice rectum, and that's your C value. All right. And then how do you find the directrix? We'll add, subtract, depending on which way it's going, right? And the directrix is a what?
Line.
It's a line, right? So make sure you don't write, like when you write the vertex, you're writing a point. Don't do the same thing with the directrix and write a point, because it's actually a line. All right? Okay, so let's take a look at ellipses and hyperbolas. Now, hopefully you have some knowledge of this floating around in your head. I have students that hate conic sections. Like I have some that, like Clara at 7th period, she's like, ugh, I hate conics. Just hate them. I mean, sometimes you just hate stuff. I got to be honest, there is very, very little interesting about conic sections to me. I mean, I guess if you go into the military and you're working with radars and stuff like that, that there are elliptical patterns that get sent out and you might have a use for this, but on my life, I can't think of all. And there are things in physics where you have parabolic, like projectile motion moves in parabolic patterns and things like that. So there are occasionally, or profit curves, you might maximize a profit function, a parabola. But for the most part, it's just learning stuff, memorizing stuff, and I get it that it's kind of boring. The upside of it is you can do pretty well in this test just knowing facts. So if you're one of those that does well with Quizlet or flashcards, get busy on those, figure those out and get them, and you can probably do pretty well just on the factual part of this test. But yeah, there is a lot of stuff, as you can see. So I'm going to show you the relationship between ellipses and hyperbolas and just get all of that out there today. And then there might be a couple of new things. I kind of forget what we do in Algebra 2. There might be a few new things. Like I don't know if we did the directrix. The directrices, actually there's two of them, of a hyperbola and ellipse. It's not even in your textbook. I didn't even know these existed until we got a Vestavia question. I was like, what the heck? So then I did a little research, and sure enough, they exist. So I've added that in there just to make sure we can get those, but even though I don't count it very, very much. But there's a lot going on here. Oh, another thing I didn't mention. Eccentricity or eccentricity, depending on who you talk to or who you listen to, that is a measure of shapes of conic sections. And one thing I did not mention is the eccentricity of a circle. It's kind of easy to remember. The E is always 0, which is nice because it's a circle, right? And the eccentricity of a parabola is always 1, okay? And if you're wondering, like, if it's a measure of the shape, you could say, well, why is it always 1? Well, if you look at a parabola, I don't know if you know this, but there are really skinny parabolas and then there are really wide parabolas, right? But I don't know if you know this, but like any parabola going up, I can zoom in or zoom out on it and then take that shape, depending on how much I zoom in and zoom out, and make it fit perfectly on any other parabola. So technically, like, for instance, if I had this really wide parabola right there, and I had a really skinny parabola right here, if I zoom in on this thing right there, I can make it look exactly like that thing. So in some ways they are related, and that but I can't do that with an ellipse, right? If I have a really skinny ellipse, can I zoom in on it and make it look like a really fat ellipse? No. So, but I can on these, and if on this one right here, I can zoom out on it. And if I zoom way out on it, eventually, from a perspective far away, it will seem really skinny from a far away distance. Is that kind of making sense? Well, that's kind of why these, and obviously a circle, you know, is a circle no matter how you look at it. So that's why these are fixed eccentricities, is their shapes are really kind of the same, all of them, from a perspective. But that's not true on hyperbolas and ellipses. So ellipses falls in between these. An ellipse, and we'll talk more about that in a second, the eccentricity is measured by the C value over the A value. And that'll make a little bit more sense when I remind you about what C and A is. And that ellipse value always ends up being in between, sorry, not equal, in between the 0 and the 1. So 0, circle, parabola 1, and anything in between would be an ellipse. And then a hyperbola, I can fit this in there, a hyperbola is also measured by C over A, but it is anything greater than that 1. So really, can you see it? So along the whole spectrum here, we've got 0, eccentricity 0 here, 1 here. That's been arguably one of the more common ciphering questions. What's the eccentricity of a parabola? And I always see people working really hard, and I'm like, what are you doing? Like, I don't even know what they're doing. But this is always 0, always 1, and then an ellipse will vary depending on the C and the A, and a hyperbola will vary. And generally speaking, the skinnier it is, a hyperbola, the more elongated it is, the closer it is to 1. The more round it is, the closer it is to 0, which kind of makes sense, right? Because the more close it is to a circle, the closer that E value gets to 0. So really skinny, stretched out ellipses might be 0.9, 0.95, 0.7, actually a 0.7 is really going to seem pretty ovally. But closer there, skinny, closer there, circular, and then on a hyperbola, the bigger it gets, the more skinny it gets this way. So it might look like this, if it's like E equals 1.2, and then it might look really skinny looking like this, if it's E equals 5 or 7 or 10 or something like that. You tracking with me? Okay, so that's eccentricity or eccentricity, depending on how you want to say it. And let's just walk through these, and I'm going to talk about the similarities for you. Now, when you look at these formulas for ellipses, these two terms, first of all, it has to be equal to 1. If it's not equal to 1, then this stuff doesn't mean anything. So like if this was equal to 10, I would have to divide everything by 10 to make it equal to 1 for these values to actually make sense in what we're doing. Okay, so when you're completing the square, which I'll talk about in a second, your end game is to get over here and get this value on the right equal to 1, and then make it look like this form. And I'll walk you through that process. And this process for an ellipse will be the same as it is for a hyperbola. Okay? Except here you're trying to get these terms, and it really doesn't matter what comes first because they're both positive. So it doesn't really matter to me. I typically put the x value first, but it doesn't really matter on an ellipse. Now, do you remember these values right here? Why I call one of them A and one of them B, or if there's a significance there? You can see like here the A is with the X, but here the A is with the Y. A is bigger. Now that's not true for a hyperbola. I put it in here, A is bigger. So if you look up here and there's a 25 there and a 16 there, then the 25 is the A squared, the A would be 5. If you look over here and you've got a 9 here and a 12 there, then the A squared is 12 and the A would be root 12 or whatever, 2 root 3. Are you seeing that? So here the A is always bigger, and the A value is going to show you the biggest stretch. Do you remember when you're graphing these, what these two numbers do when you're graphing? Do you remember? So if I have the A and the B, what does the A do? The A moves either that way or that way, and you can tell based on what it's under. So this particular one right here, I'm actually graphing this graph right there. So you can see, I've used all this information to fit those equations. So right here, because the biggest one is 25, and because that's below the x, I'm going to move 5 each way on the x. You with me? From whatever the center is. And then on this one, the other value, the 16, that's your b squared. Everybody tracking with me? So that means the b is 4, and since that's under the y, I'm going to move that way up and down. So if I have the vertex, which I can find easily, right? 3, -2, and I go and I mark that, I move left and right 5, up and down 4, and what do I do to draw or sketch an ellipse? Connect the dots. Well, not connect the dots, because that would give me a diamond, but try to draw an oval in there. So literally, when you're graphing this, you're going to find the vertex, or the center, go over A, up B, down B. I think I marked, up B, down B, and then I'm going to just connect those 4 dots in as close to an oval as I can. And I realize some of you have some graphical impairments, and you always start really strong, and then a lot of times it turns into the dreaded, I don't know what it is, broken baseball diamond or something, I don't know. But anyway, try your best to make a decent looking oval out of it. And remember, if my A value moves more up and down, which you'd know because the biggest number would be under the y, then you're going to end up with an oval this way. But you really didn't have to think about the direction of it, did you? I mean, when I think about it, like I'm saying, you didn't have to look at the problem and go, all right, now I got these 4 points more, which way is it going? You didn't really have to think about that on an ellipse, because once you mark the 4 points, you just connect the dots. And if it's stretched more this way, you'll go, oh, look at that, it's stretched more this way. How about that? You with me? That's not true on a hyperbola, so that's why I'm mentioning that. Now, there are other parts of a ellipse that are important to find, and that basis it's based on the real definition. Do you remember the little string example I did last year? Where I took the string and I marked the 2 foci and then I traced it around and it made an oval? Okay, that's the real definition of an ellipse. And the real definition says all the points on the curve where the sum of the focal radii is the same. And the sum of the focal radii, like if I had a focus here and a focus there, and I said, all right, if I took a length of string that's, I don't know, 15 inches or something, and I connected it there and there, and I stretch it out, it's going to give me all kinds of points, isn't it? All kinds of points on this. And all those points, if I mark every one, form an ellipse. But I'm not going to sketch it that way. It's impossible. You're not going to be like cutting a piece of string out on your test, and pinning it to your paper and drawing a little trace. So what we're going to do is just guesstimate with those 4 points. But I'm still going to ask you about stuff like where's the foci? All right, or where are each of those? So how far away is each focus from the center? C. And the nice thing about that is that's kind of true for a vertex a focus on a parabola as well, right? How far was the focus from the HK on a parabola? That was your C value. Well, same thing here, except the HK is now the center, not the vertex. But that distance to the focus is C. Well, where does C come from? It's obviously not the same thing as a parabola because it's not a parabola. Well, C comes from a relationship between the A and the B value. Does anybody remember that? I showed y'all a little trick to do these with ellipses and hyperbolas. With ellipses, if you take the A squared and the B squared, and whatever that is, change the sign, it's equal to C squared. Are y'all seeing that? And then if you take that's an ellipse, on a hyperbola, it's the same thing. You take the A squared and the B squared and you change the sign and you get the C squared. So that there's a formula in your book that doesn't look that way, but I think that's the easiest way to remember it. So back to what I know about ellipses, if I've got an ellipse and I want to know, all right, where are these foci? I've got to know the C value. So all I got to do is go, like on this particular example, I'm going to take the 25, which is the A, the 16, which is the B, subtract them, and I get C squared. A squared minus the B squared. Are y'all seeing that? So what do I end up getting for C? I end up getting 9, so square root c squared is 9, c is 3. And you don't always get a pretty number, but you did here. Are you seeing that? So now I know that the focus is c away from the center. Now how do I know to go left or right or up or down? Whichever way the graph's going, right? Or whichever way the A went. Because the C is always on that A line, whatever you did for A. So right here, I'm going to go, all right, now I can find the focus. I just go down here, and I take my center, and since I'm already stretched more this way, I go 1, 2, 3, 1, 2, 3, and I've got my 2 foci. Now, if it's me, sometimes your C value is ugly. Like, what if your C value was root 10? Like, what if? But I still want to know what the foci are. Well, aren't you starting at 3, -2 with the vertex? That's the vertex, right? Now, didn't you go right and left? So if I go right and left, what am I doing? Am I changing the y or the x? I'm changing the x. So all you would have to do for the focus is take that 3 and go right and left to get your 2 foci points. Does that make sense? But in our problem, we had it kind of easy because the C was 3. I mean, I could graph it and then just go, oh yeah, 6, -2, 0, -2. But look, even with this, I could still think go right and left 3, and it gives me 6, -2, and 0, -2. So when your C value is ugly, like a root, which it likely is, or not likely, but it possibly is, make sure you still have a plan. And if it's a radical, you can't simplify it, so you could just leave it. 3 plus or minus root something. But in this case, you can clean it up, and we always want to clean it up. Tracking with me? Okay, so those are foci. You already know about the center, which is the HK. Now there are some other values too on this. The values at the endpoints of what we call the major axis. You remember the major? How far is that major? How long is it? What's the length from here to there? 2A is the major, and what's the minor?
2B.
Right? And remember, the major is always the biggest one. Sometimes the major is going up. At the endpoints of the major, these are actually points, and they have names. These do not, at least not that I know. So these points, guess what they're called? Vertices. Each one is a vertex, which to me kind of seems normal, because if you think about that's a focus, and here's the graph, what does that kind of look like, just this part of it?
Parabola.
Kind of looks like a parabola with the focus right in the middle, right? And it kind of looks like a parabola here. Now, it's not a parabola, but if you're trying to associate, yeah, the vertex would be right there on the parabola. There would be the focus. The vertex would be right there. There would be the focus. It kind of looks like two coming together, even though it's not. So that might help you to remember that those are vertices, and these don't really have names. So if I asked you to find the vertex, and you know that, how far do you have to go to get to the vertex? A, because it's at the end of the major axis. What could you do? You already know that A is 5. What could you do right here if your A is 5? Sorry, I put V equals 3, -2. That's the center equals 3, -2. What could you do to find the vertices? You could start with this and just add or subtract what? The A value. And in this case, you get 8, -2, or -2, -2. Now you could see that here, right? 8, -2, -2, -2. But again, if your A value is ugly, like a root 7 or root 21, well then you could just say 3 plus or minus root 21, comma -2, call it a day. And remember, if it's stretched this way, what are you adding to or subtracting from? Instead of the x coordinate, what would you be doing? Adding or subtracting from the y coordinate. Y'all seen this so far? I know I'm throwing a lot out there. All right, so that gives you almost everything. There's one, well, maybe not almost everything, but a lot of it. There's one other thing I want to talk about. Do you remember the latus rectum from the parabola? And we said the latus rectum was the width of the parabola at the focus. Well, latus rectum, there's one on a parabola because there's like one focus, but there's two on an ellipse or a hyperbola because there's two foci. But they're the same length. It's that length and that length right there through the focus. Now I used to make this a hard problem. I didn't make it a hard problem, but I used to say find the length. And you know what people did? They came over here and they found the focus, and they took the x value of that and they plugged it into their equation. And they solved for these two y values. And maybe they got y equals 1 point something, and maybe y equals negative 5 point something. And then they used those two values and they subtracted them to find that length. And I was like, that's so awful and so tedious. So I played around with some variables and I came up with a little formula. So I found a generic formula that works for you, and all you have to know is your a and your b value. So the length of that latera recta, or each one of them, is 2b squared over a, and I wrote that somewhere maybe? There, right there. So the length of each of those latera recta, 2b squared over a. So that's a much easier way to find the length of the latus rectum here and there, whether it's like that or whether it's going up or down. It's much easier than actually plugging in a coordinate of the focus to find where the points hit and then measuring the length there. So much easier, in my opinion. Are you with me? And then remember we talked about area yesterday? If you weren't here, we talked about how a circle, we don't really even think about area of a circle. We just go, oh yeah, it's pi r squared, right? We kind of know that from geometry or before. But if you really think about it, it's pi times that length times that length, pi r. Well, if you think about area that way, then when I have an ellipse, it's pi ab. It's similar in how it's calculated. So this is probably a better formula, pi times the radius that way, the radius that way. Pi times the radius that way, the radius that way. But if you remember that, that's the formula for the area of the interior. So the only thing I've left off at this point is the sum of the focal radii is always 2a. I don't know if you remember this, but let me kind of walk you through it. Pretend there is string right here, okay? And I have my string right there and right there. What happens if I bring this string all the way to there? As I'm bringing it, it's moving like this, right? Now once it gets to right there, tell me, is my string doing this? It's going all the way to there and then back, right? Now what happens if I cut that small piece off and put it right here? What does that tell you about the length of that string? It's the same as the major axis. And you already know the length of the major axis is AA. Well, what that means is the length of my sum of focal radii, and by the way, again, the sum of the focal radii is the sum of the radius, the focal radius. And the focal radius is from there to there and there to there added together. Well, that's the length of the string. So the sum of the focal radii, the string's not changing length, right? It's always 2a no matter where you go, because it's always the same length as the major axis. So all these facts you're going to have to remember, and they're annoying, but some of the questions you're going to get asked are going to be very basic, like, hey, given this ellipse, what's the sum of the focal radii? What's the length of the minor axis? What are the values of the foci? All that junk's just going to be thrown into a problem like just A, B, C, D, E, F, G, or whatever, or 1, 2, 3, 4, 5, 6, 7. And then there are going to be little 3-point questions. Boom, 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 boom. Y'all with me? And then sometimes I'm going to give you information like just enough to help you. Like I'll say, hey, by the way, the major axis has the length of 24. What are you going to get out of that? That A is 12. And then I might go, hey, the sum of the focal, the length of the length of the latera recta is 10. You're like, oh. The length of the latera recta, 2b squared over a, is 10. But wait, I already found what? That a was 12. And you can plug that 12 in there, and then you could solve for b, right? So now you have a and b. And then I might say, well, what's the value of c? Well, what do you know about c? It's always a squared minus b squared. So now you have your c. And once you have your A, B, and C, you have everything you could possibly need to either graph one, find your focus, find the length of anything. I mean, you name it. Find the vertices. You name it. I can find anything once I have my A, B, and my C. So those are the kind of questions I'll give you just enough information to be able to put it together, figure out everything you need to know. You track with me?
Sure.
Okay. All right. Let me take one more glance. Oh yeah, and then completing the square. When you complete the square with these, how do you look at this thing and tell that it's not a circle and not a parabola, and that it has a shot of being an ellipse? You know it's not a parabola because what? There's two squares. So that's off the table. You know it's not a circle because these coefficients of the square terms are different. And you know it's not a hyperbola because on a hyperbola, even though we haven't talked about them directly yet, what happens? One's positive, one's negative. So because they're both positive but different, it's kind of like a circle, which is what an ellipse is, or actually technically a circle's a kind of a form of an ellipse. So I'm looking at this and going, I'm betting it's an ellipse. Now, is it guaranteed to be an ellipse? Why not? What could happen? And it's similar to a circle. Yeah, it could end up being degenerate. What does it mean to be degenerate? When I'm completing the square, what ends up happening over here? All that cancels and I end up getting a 0 at the end. And if that happens and I get a 0 right here, first of all, go back and check your work, because there's a chance you make a mistake, right? We all make mistakes. Go back and check your work, but if you do get a 0, you're like, wait a minute, that's a degenerate conic. And what would a degenerate ellipse look like? It'd look like a point. It looks like a point just like a circle does, because it's related that way. Now, what happens if you get down to here and you end up getting a negative number? Like, what if this ends up being negative 400? Then this can't even exist. Because think about it. Can you square something, which is going to make it positive or 0, and then square something else, which is going to make it positive or 0, and then add them together, which is going to make it positive or 0, and get a negative? It's impossible. So you would say D and E. So you don't know for certain that it's an ellipse. It probably is based on the likelihood of a problem being given that's not a degenerate, which is most of the time. But it's possible that it is. Okay, and you wouldn't know. It's a great math team question. They go, what is this? And of course it's like circle, ellipse, blah, 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 and then none of these. And if you just get real happy and go, oh yeah, ellipse, sweet. Well, you may be right. I mean, I definitely know it's not any of the other ones, conics, but it could be degenerate and it might not even exist. So you do need to complete the square. So just like a circle, the only difference would be, because these two numbers don't match, like they did on a circle where they were both 3, I really can't divide them out, can I? I mean, I could find a common denominator and divide them out, but then I get ugly crud in the bottom, in the denominators that's messing with me. So what I would rather do is leave it in there, put your x terms together, your y terms together, and then just factor it out. Factor out the 16 and the 25, and just leave them there for a second. All right? And then complete the square, but don't forget, if I add 9, what am I really adding? 16 times 9. If I add 4 here to complete the square, what am I really doing? Adding 100, right? And then once I get to there, I'm almost done. How do I make this work for ellipses and hyperbolas? Because it's got to equal 1. So whatever that number ends up being, divide all 3 parts by it. And when you do that, you're going to see most of the time this stuff cancels really nicely, right? And gives you a nice, neat parabola. And if it doesn't cancel, do something like this. Like what if I had some, what if that was a, what if this was 12? Does 12 go in there? No. If that's a 12, couldn't I say, all right, when I divide by 400, 12 divided by 400, if you really think about it, if right here I multiply the top and the bottom by a 12, or 1/12, which I can do, right? Wouldn't that cancel this and just put 400 over 12? So if you don't see them cancel perfectly, all I do is take the 12 on the top and put it below the 400, because that's what ends up happening, 400 over 12. So if it didn't cancel, I would just go, oh man, it doesn't cancel nicely. All right, I'm just going to put it under there and simplify it as best I could. It's just a little quick way to deal with it. All right, the only thing I have not talked about is this, and I'm going to come back to that. I'm just going to come back to it. But I think I've talked about everything else here. So let me jump and emphasize the differences on hyperbolas, okay? Because there's a lot about them, even though the graphs are completely different. You might remember these. Okay, first major difference. On a hyperbola, the a is not the biggest one. The a value, the a squared value, unlike a in an ellipse, is not going to be the biggest of the two values. It's not. Do not think that or everything goes south. And I mean everything. Because then anything to do with A or B or C is going to end up being wrong. Actually, not C, but everything else. So right here, it's whatever comes with the positive term, not the negative one. That's your A value. And since I always like to put the positive first and the negative second, as do most books, the A value is going to come first. So it might be something like 4 and 9. It might be something like 25 and 16 or whatever. But here, the A is 2. Here, the A is 5. It has nothing to do with the size of the A value. Are y'all with me on that? So once you find A and B, this part is the same. Whatever's under the X, what do? If A is under the X, move that much under the X. Or whatever it is, whatever number's under the Y, since that value is, since your B is 3, move that up and down the Y. That part's the same. If this number's if 5 is under the Y, move up and down 5. If 4 squared is under the X, move left and right 4. So when you do that, you have 4 points and a center, just like you did on an ellipse, right? Well, what changes? You don't just connect the dots, that would be an ellipse. So what do you make out of those 4 dots? And why do you make that box? Because, right, the corners guide your asymptotes. Remember that? So, based on this hyperbola down here, this one that we did, and I'll come back to completing the square, you can see here that the value below there, it came first, so that's your A. Not because it's bigger, but because it's first. The 16 came second with the negative term, that's your B. So I'm going to take 5 and go 1, 2, 3, 4, 5 each way. You can see that right here. And then I'm going to take 4 because it's below the Y and go up and down 4. And those 4 dots give me the top and the left and the bottom and the left and right of my box. So I'm really careful to draw nice horizontals and verticals so that I can really see where these endpoints hit. And keep in mind, sometimes your A and your B values aren't going to be nice perfect squares right there, or nice neat numbers. They might be root 7. So if it's a root 7, go up about 2 point something. If it's a root 12, go up about 3 or whatever, point something. Y'all seeing that? Okay, so once I do that, you make your box, and then these corners on the box, that's where you sketch your, I was about to say astropoles. I did a question once like, what's the name of the diagonal lines on a hyperbola? And some kids like, astropole. Anyway, I thought that was fun. So draw your asymptotes in there, and what are the asymptotes doing for you? They are guiding your graph out. So really, that's all you need to know is once you have them in there. Now, I have a question. How do I know, well, I mean, why is this thing opening to the right and the left here? Because my X term was the positive term and it came first. So had this been Y plus 2 squared, X minus 3 squared, and the Y came first, then I would sketch this thing from the top of the box like this and the bottom of the box. So it has nothing to do, you can't look at this and go, oh, the biggest number's under X, it must be opening. It's not because it's the biggest. It's because X came first that it's opening right and left. Now the great thing about this, the negative thing about this is there is no nice, neat sum of focal radii. There is no piece of string I can use to measure. There's a difference of focal radii. But the difference of focal radii, the great thing is, it's still 2A. So, the difference of focal radii, like the sum of focal radii, still, you find these two focus points. Like there's one right there. There's another one maybe right there. Focus, focus. If I were to measure from the focus to the graph, and then from the graph to the other focus, and subtract them, I get the same thing every time. So whether it's that minus that, or this minus this, or this minus this, all of the differences of those two lengths always equal 2A. And remember, your A value is whatever you moved to get to the graph, whether it was that way or that way. Here, it was left and right. So right here, if that's 5 and that's 5, this length right here is 10, that 2a, that's also the length of that difference of focal radii. Now we don't call this the major axis, the part that connects the vertices. We called it the major axis on an ellipse because it was bigger, but it's not always bigger here. So what do we call it here? What do we call it here? The transverse axis. The way I remember that is like a transcontinental railroad connects two parts of the continent. A transverse axis connects the two parts of the hyperbola. And then what is a conjugate? It's the other one, kind of like 2 plus I, the other one's 2 minus I. Well, the conjugate is the other axis at major length right there, and it's 2b. So the 2a is always the transverse, the 2b is always the conjugate. These also have degenerate situations, but a degenerate hyperbola, again, if you're completing a square right here, if I'm completing the square and I get all the way down to here and I get a 0, it's a degenerate. But guess what it looks like? Do you remember this? It's not 2 points. Guess what it is? It's the asymptotes. So it ends up being a pair of intersecting lines. So an X could be just 2 lines, or it could be a degenerate hyperbola. And can you ever, what would happen if I got a negative 400 here? If I get a negative 400, does that mean that this does not exist? No. Why? Because I can subtract 2 things and get a negative. So if you do get a negative on a hyperbola, don't fret. Just divide by a negative 400. I'll still get 1 like I like it, but what happens here with these 2 negatives? They become positive, and then this term would end up being what? The negative term, so I would just switch places. So if that ever happens, you don't have to worry about this not existing. Just take the negative term and put it there, take the positive term and put it there. And that's different, because these might actually not exist, but ellipses and circles, I mean, these actually will exist in all circumstances, whether it's degenerate or whether it's a hyperbola. All right? Got 5 minutes. All right. So we've talked about a squared, b squared, c squared. So what would your equation of a squared, b squared, c squared be with this? A squared, change the sign, b squared equals c squared. What's the length of the focus from the center? C, just like before, that part's the same. What's the length of the vertices from the center? A, just like before, all that's the same. So they look a little different. Right here, this would have been an ellipse, right? And that would have been that would have been A on an ellipse, and then your foci would be in the middle, and that would have been C. Well, here, your foci are on the outside, but it's still C. From center to focus is C, and from center to vertex is A. That's the same. Center to vertex is A, center to focus is C. So those parts are the same, it's just how you find that C that might look different. These also have length of a lateral rectum. What's the lateral rectum or lattice rectum measuring? The width of the opening where? At the focus. I did the same thing here and found the width, and guess what I got? Also 2b squared over a. So each length can be found using that formula without this pain and suffering of finding the focus, taking its coordinate, plugging it into the equation, finding the 2 values there from it, and then subtracting them. So much easier just to throw your stuff into there. I know. It's just too much information. When are we ever going to use this? I totally hear you. My hands are tied. I have to follow the course of study. And then bludgeon you with. And then, what was I going to say? The only thing I was going to mention on this completing the square, you really don't know when you start whether this number on the right is going to end up being positive or negative. You don't. On an ellipse, it ends up being positive most of the time. On these, 50-50. So what I normally do is just say, you know what? The y squared's negative now, so I'm going to put that negative term to the right, take the x's, they're positive to the, or at least the x squared's positive, and then I'm going to factor out like I did before. But when you factor out that negative, what do you have to do to this? Make it positive, complete the square, but when you do, remember 16 times 9, negative 20, negative 25 times 4, negative 100. That's why a lot of times this, because you're negating it over here, a lot of times you end up getting negative values. But in this case, you ended up with positive, and then like before, divide by that because you have to have it equal to 1. And then if everything doesn't cancel, again, if this had been something like 11, what's a quick way to deal with that? If it doesn't cancel, all of it doesn't cancel? Yeah, just put the 11 beneath that and make that your, either your a, well in this case it'd be your b squared. Yeah.
So is that the whole unit? Is that everything?
That is almost everything with the exception of directrices. And I'm going to come back tomorrow and talk about equations of asymptotes because those can sometimes be tricky. You tracking with me?
Sure.
Okay, so tonight, guys, you should be able to finish up your first and your second review, or Sunday night, or whatever. And at the very minimum, I got a kind of a work day, maybe a play day built in. When I say play, I might pull out the conic sections game. Ooh. All right, but I've got a Wednesday. I got a Wednesday to play with, but I need you to come with good questions. Follow the assignment sheet, but come with good questions on Tuesday. I'm sorry, on Monday. And we'll try to get you straightened out.